are going to go over the force of gravity's post-lab. All right, let's begin. So, a couple of very important things about this lab. This lab is very foundational for the rest of the year. The force of gravity will show up no matter what unit we're in. Um, we get to now add it to the kinematics unit when we throw the buggy and the carts in the air, right? So everything here on Earth has a force of gravity acting on it. So, without further ado, let's begin. So, up until this point, we called the force of gravity the force of the Earth, right, on the object. Okay. Now, here's a couple of things. That is synonymous with just saying F of G on the object, or simply the weight of the object. All right. So all three of these things are synonymous. They are equal to each other. Now, it is very important. Okay, so important. I'm gonna bring out my rainbow pen. This is very important. Weight is equal to the force of gravity, and it is equal to the force of the earth. It is just three different ways of calling it the same exact thing. Now, the other extremely important thing, okay, let's bring out my Galaxy pen one more time, is that weight, which is equal to force of gravity, which is equal to the force of the earth. Yes, I know I'm rewriting it, but here's the important part, does not equal mass. All right. So mass, by definition, is um, it is the, the substance that makes up an object. And by substance, I mean like all of your atoms, right? So you're made up of mass. You're made up of this physical thing, and you combine millions and trillions and billions of your atoms together, and we make up a human being, right? And we can make up any object using this idea of mass. So the important thing is that mass, it never changes unless you physically remove part of the object. So what this means for us, let's say, I don't know, we have, you go to like the carnival or like the state fair, and you get one of those uh, giant teddy bears. This looks like a teddy bear, right? That's a teddy bear color. Yeah, there we go. All right, so you get one of those giant uh, teddy bears. Let's see. Let's draw a giant teddy bear there. All right. Oh wow. You can tell it's been several years since I've won a giant teddy bear. Okay, so this is a giant teddy bear, and I hope that you at home are also drawing this giant teddy bear. All right. And let's say this giant teddy bear has a mass of about 10 kilograms. Oh my gosh, that's pretty heavy. All right. That's roughly like 5-ish pounds. Okay, so the mass of the teddy bear is 10 kilograms. And notice here the mass is represented with the variable m. Okay, and we can say that the weight of the teddy bear is roughly 100 newtons, and we'll go a little bit into more detail about this, right? So we should have covered this in the lab right there. The unit of measurement for the force is in newtons, named after Sir Isaac Newton. All right, so if we, let's say, chop off a arm of the teddy bear, whoop, right, and you remove it, and you burn it, and you send it off into space. That means that the teddy bear's mass decreases, and so does the weight. So when you physically alter the object, the mass changes, and so does the weight. But let's say we take this teddy bear and we go to a different planet. Let's say we go to the moon. All right. So this is the weight on Earth. And that's why it's so important that we call it F of the Earth. Okay. Or the force of gravity um, of the Earth. Right. So the Earth here is important. So if we go to the moon, the object on the moon, so the mass of the bear on the moon, so let's say this is all the earth stuff. The mass of the bear on the moon is still 10 kilograms, right? So this is the bear as a whole. We didn't chop off the arms or anything like that, right? The OG bear. The mass of the teddy bear is still 10 kilograms. But look what happens here. The weight, the force of the moon acting on the bear, okay, is not 100. It'll be more like 16 newtons. Okay, so the weight of the bear changes on the moon because the force of the moon acting on the bear is less than the force of the earth acting on the bear. The earth will pull on the bear more than the moon. That's why if you watch old clips of astronauts on the moon, they seem what we call quote unquote weightless. They're not actually weightless, they just weigh less. Whoa, you see what I did there? They're not weightless. Okay, they're not weightless on the moon. Okay, they actually do have weight on the moon. They just weigh less. Oh my gosh, I'm so good with this. Oh yeah, they just weigh less on the moon. They're not weightless, and that's important because that is actually one of the things that many students get wrong on the physics stuff. Okay, you're not weightless on the moon. You just weigh less. However, you are weightless in space. So back to the lab. Um, for the lab, we had a graph, and we said it was the force in newtons, and we had the mass in kilograms, right? And you should have gotten so force mass. You should have gotten a slope, and this slope would be equal to roughly 10, okay, the value of 10. So let's break this down. How do we get this? Well, what this shows us is that, I'm going to use a different color pen here, is that no matter what your mass is, okay, no matter what your mass is, your 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 force or your weight will adjust accordingly. And when I say accordingly, we're talking about a ratio here. Okay, so you see these dots I'm drawing; those are the different masses that you put on this scale, right? So no matter what your mass is, the weight of the object will adjust accordingly, and there's a special ratio for that. And that ratio and that number is that slope, is that 10. And what that 10 is G. G is 10, and that's not like a special or a different letter or a common letter G. This is a very special letter G. This G is the acceleration due to gravitational field strength. Oh my gosh, yeah, that's a mouthful. Okay, this is the acceleration due to the gravitational field strength. And so what this means is that whenever you drop a object here on Earth, the object will accelerate with this value of 10 meters per second per second. And so another way of writing this is A sub G is equal to 10 meters per second. Or a quick way to write it is just 10 meters per second squared. And this number is so fundamental for us here in our physics class that it is on your formula sheet. And I'm going to highlight this. It's very important. This is a very important formula. You need to have this memorized, right? Now, it is not gravity, okay? Now, that's one thing I need to point out. When I ask you, what is the acceleration due to gravity? Okay, you should say 10 meters per second squared. But if I ask you what is your vertical acceleration here on Earth, you can't say it's gravity, right? So gravity by itself is not the appropriate definition for 10 meters per second squared. It is the acceleration due to gravity. And let me show you why. So at the very, very beginning, we were discussing all the different ways that we can call the force of the Earth, right? So the force of the Earth is also called the weight, and it is also called the force of gravity. Okay, now the force of gravity does not equal to the acceleration due to gravity. The two are not the same. So if I ask you something, 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 and your answer is gravity, you will be wrong because you need to be specific. Are you talking about the force of gravity, which is talking about how hard the Earth is pulling on the object, or are you talking about the acceleration due to the gravitational field strength, which is how much the object will speed up or slow down here on Earth? Remember, acceleration is all about speeding up or slowing down. Okay, so the answer of gravity will not be accepted. In fact, if you write it down as just gravity, I will mark you wrong because I don't know what you're talking about. So you can either talking about the force of gravity or the acceleration due to gravity. All right, so now let's go back to the lab. So with this graph, you should have gotten a slope of 10, and that 10 is the acceleration due to gravitational field strength, and it is 10 meters per second, and that is for here on Earth. On the moon, it is less. Okay, the moon. So the acceleration due to gravity on the moon, I believe it is like 1.6 meters per second. Okay, it's is significantly lower than here on the Earth. So, with all that being said, we can actually come up with the formula for the force of gravity. Okay, this is just a generic force of gravity formula. We can say so. We draw this here. This is force. This is mass. Force in newtons. Mass in kilograms. Okay. And we said that the slope is equal to g, which is 10 meters per second. And remember, for us here in physics, whenever you are talking about slope, okay, slope is equal to the change in the y-axis over the change in the x-axis, or rise over run, and our y-axis is F, right? Force divided by the change in the x-axis, which is mass. Okay, and all that equals to this acceleration due to gravity g. Okay, and that was for our lab. But if we were to use a generalized formula, we would just say it's a. Okay, a equals F over m. And in fact, this is so important. This is a huge foundational formula for us in this class. There's a very specific name for it. This is called Newton's second law. Okay, Newton's second law. And in his second law, you'll see it mostly written as force is equal to mass times acceleration. But on your formula sheet, you will see it written as A is equal to F over M. All right, so the general mathematical formula is what you see on the right. Newton's second law is just that formula rearranged on the left. And remember, we got this from our lab by taking the slope. Okay, and we said that the slope was equal to the acceleration due to gravity, which is 10 meters per second. Very important number. And with this number here, okay, let's make another connection. With this number here, this number tells us the force of the Earth, aka the weight acting on the object, and we can rewrite this formula as m times g. Okay, and this is strictly for the force of the Earth acting on the object, mg, which is also the formula for weight. Weight is equal to mg as well. All right, a lot of different formulas there. We will get a lot of practice with how we can use this mathematically. Okay. Until then, see you next time. Bye bye.